Welcome to the Philosophy Forum, and at least for the time being, to the last student faculty seminar of the President's Lecture Series. As you know, this has been a place of instruction, of illumination, and of intellectual fireworks. And the person to whom we owe all this is Richard Drake, and tomorrow he will begin a new phase in his academic career when he will be installed as the inaugural Lucille Spear Research Professor in History and Politics. This will take place at 4:30 in the Del Brown Room of Turner Hall, and you're all invited. So his investiture will take place tomorrow, but right here and now is the time to express our gratitude and admiration to Richard Drake for the 31 years in which he has organized all this. So please join me in recognizing there couldn't be a better presenter to indicate the depth and width of the faculty seminar of the students of the President Lecture Series and of the President Lecture Series themselves as Professor Sir J. Fraser Stoddart. Evidently, Professor Stoddart has been elevated to the knighthood, and he is the 2016 Nobel Laureate in Chemistry. There's much more, and you will hear about it this evening when Professor Stoddart will speak about art and science, mingling art and science, and that will take place in the University Center Hall, the University Center Ballroom at 8 o'clock. His topic this afternoon is the rise and promise of artificial molecular machines based on the mechanical bond in chemistry. Please join me in welcoming Professor Stoddart.
Well, thank you very much, if I may call you so, Albert, for your introduction, and also Richard, wherever you are up there, for all the hard work that you've put in over the last year to have me come to Montana for the first time. I'm having a wonderful time. Thank you. So, the mechanical bond. Let's start just with the noun bond. It means different things, of course, to different people. Chemists, of which I'm one, do not have a monopoly on the definition of a bond. Financiers use it, biologists use it, social scientists use it, anthropologists use it, and if we slip the adjective mechanical in front of it, it's not the exclusive prerogative of the chemists. One finds examples, and I'll show them probably tonight, in our daily lives and in nature and art and architecture. And then in a more light-hearted vein, of course, we've all met Bond in the cinema. And this first one here, Sir Sean Connery, when I went to Los Angeles in 1997, in the intervening years, I was mistaken on 2 occasions in the street for Sean Connery. So you might be asking, what is a mechanical bond? It's a reasonable question given the title of my talk. And the 2 most archetypical representations at a molecular level are a catenane and a rotaxane. So the simplest one, 2 interlocked rings, and the simplest one here, what we call a dumbbell, and one ring entrapped on that because these stoppers are too big to allow it to depart. I did not coin the term. It was coined by Professor Frisch, I think in Albany in the New York State University system, even long before molecules of this type were made. What I want to get over to you is, in chemistry, a new chemical compound is probably visiting the world at the level of several tens of thousands a day. A new chemical reaction, that might be, I don't know, a dozen a year. It depends what restrictions you put on the definition. But a new bond in chemistry that is in equal strength to a covalent bond, that's only once in a blue moon. And so it's really this once in a blue moon that I want to share with you today. So a little bit more about catenanes and retaxanes. I call them mechanically interlocked molecules, or MIMs for short. And here is the retaxane as defined in Wikipedia. You can see that it's derived from Latin. And Wikipedia gets it right. They're molecular. They're molecules. And this I must stress. And likewise, Wikipedia get it right with the catenane. They're molecules. And you see images here that I guess everyone will be familiar with. The abacus, which is not unrelated to the retaxane, and a symbol that we're all familiar with. And so I'll just use that symbol to go in at the deep end, or maybe I don't. Let me see what I'm doing. I'm establishing molecular recognition, template formation of catenanes and retaxanes, and then we'll look at molecular shuttles and molecular switches, and then things called energy ratchets, a type of templation that is radical in nature, and then a molecular machine that is a pump. And we'll be doing chemistry away from equilibrium. And scientific discovery is not yet predictable, nor should it be. Okay, so I was anticipating what's in my slides tonight. This is a little bit of a problem when you give 2 lectures in one day. Anyway, back onto the theme. There has been an area since the early 70s that has become known as supramolecular chemistry, or relates to complexes. So an example of this is this situation down here, where you see a red ring with a blue rod, and there's nothing to stop this blue rod going in and out other than weak interactions. We call them non-covalent interactions. They may be things like hydrogen bonds, or aromatic pi-pi stacking interactions, or many, many things. I call this a pseudo-retaxane because it's on the way to a retaxane. We just have to add big stoppers, or we have to take this rod and bend it into a ring to get to a catenane. And so in making the bridge from this area of supramolecular chemistry into mechanically interlocked molecules, I'm suggesting that the mechanical bonds are made at the frontier here, courtesy of molecular recognition, which is also sometimes described maybe inappropriately as self-assembly. And the nature of the synthesis becomes that involving a template, so we often describe it as being template directed. Now, here is one of the surprising things, and I know I'm giving just a very short talk here, and I'm allowing you to quiz me for half the time. The sort of breakthrough came after I was 10, 11 years into my so-called academic career. My first appointment was at the University of Sheffield, and life was actually so miserable there that I had decided after 7 or 8 years I wanted to leave academia. When you wonder why it was miserable, it was a hierarchical situation where unreasonable people were calling the shots, the few professors, that is. And well, we'll not go any further on that front other than it gave me the opportunity to have an arrangement to go to the ICI, Imperial Chemical Industries Corporate Laboratory. And this was a breath of fresh air. This is where there were lots of young people, lots of equipment, just a great atmosphere. And at one point in my time, I came to realize that this wipeout weed killer, paraquat, which was marketed in those times by ICI. A lot of it made its way to Idaho to deal with the green potato foliage before the harvesters came in. It's very fast acting. It also will act in rain, and it is inactivated when it hits the soil. And it was a result of a collaboration that involved a very outstanding crystallographer at Imperial College London, David Williams, that led us in the first instance to look at the complexation, this is in the supramolecular world, between this weed killer diquat and a compound that is classified as a crown ether. These crown ethers were brought to the chemistry stage by Charles Pedersen, and for his invention, if you like, discovery of these, he was a Nobel laureate in 1987. So dibenzo 30 crown 10, as it turns out, wraps itself around, we discovered first of all this platinum complex where there are two amine ligands that get involved in hydrogen bonding up here, while the aromatic components get involved in what we call either pi-pi stacking or donor-acceptor interactions. Associated with this is charge transfer and a color. So these are yellowish orange. And in the presence of the company that had marketed this compound, it didn't take much wit to say, well, let's remove the platinum from the scene and let's just see if this organic dication would be complexed with this dibenzo 30 crown 10. And the answer was very firmly, yes, it was. When I returned to Sheffield, a little bit against my will, but this was at a time when laboratories like the corporate laboratory were just simply closed down by these big companies. There was no chance of staying on there. We pushed the agenda towards could we get a macrocycle that would form a complex with paraquat, this more linear of the two weed killers. And so we first of all managed to, in simple language, put blue inside red. And then, having done that, we had to, if we were going to make mechanically interlocked molecules, find out how to do it the other way around, to invert the molecular recognition and put red inside blue. It was quite a challenge to make what became known as our little blue box. And I think I have some slides to show you how, in a way, we did that eventually. But before I go there, I have some movies. So just to make it very simple for you, here is the paraquat making its way inside this red ring. So here is us putting blue inside red. And then if we just change the colors, we've got the blue box, as it's often called, and we're putting this red component inside it. But first of all, we had to make the blue box. And so here is a process by which it has been made. We used this thread containing a red unit that is a naphthalene unit as a template. So it'll play again, and you'll see we have this component here, and it reacts with another component, and during this time, all of this is encouraged by this template, which we've then got to remove afterwards in order to give us the little blue box. So that was establishing in a few short slides the necessary molecular recognition to allow us to go on to template the formation of these mechanically interlocked molecules called catenanes and ritaxanes. And so this was really our major breakthrough in 1989. Now I put some chemical structure in place. Here is the dication that you've seen on the previous movie, and here is the dibromide with which it reacts. Here is the ring system in this particular reaction that it is going to ultimately thread. But I have to tell you that in the beginning, the blue does not speak to the red. We need to have a blue unit with 2 positive charges for this to happen. And this happens as a result at room temperature in acetonitrile of one covalent bond being formed here. This bromide is kicked out and a nitrogen-carbon bond is formed. But more importantly, this paraquat-like residue is brought into place. And we saw already that paraquat likes to sit inside this red ring. And so no surprise, it apparently worms its way inside. And I use these black vertical lines to indicate non-covalent bonding interactions, which for the aficionados are sort of 4/5 CHO hydrogen bonds, donor-acceptor interactions, as in DNA, and CH-pi interactions that you often find in proteins. And then a second bond is formed that is nitrogen-carbon, and this gives us the 2-catenane with more, as it were, weak interactions or crosstalk between the ring systems and, of course, the mechanical bond. And what was really surprising, because up until this time, the previous catenane had only been made in 0.0001%, was that this was a 70% yield, as Shakespeare would say, in one fell swoop. Okay, so thanks to David Williams, we had a crystal structure where you can see from the northeast down to the southwest, you have the aromatic components, you have the bipyridinium unit, the hydroquinone rings, as we call them, bipyridine and hydroquinone, at 3.5 angstroms from each other. So again, we were very lucky. This was just as if it were made to fit the language of DNA. And then in this direction here, we have the CH-pi interactions that are there. So it's proteinaceous in that direction. And the CHO interactions involve these polyether loops and the hydrogens that are next door to the positively charged nitrogen. So here's a movie showing this. So we've already got the bipyridinium unit here. So this is the one that sucks on the ring. And then you see the closure to give us the mechanically interlocked molecule. Knocking out one bromide, covalent bond formed, weak interactions with this, another covalent bond formed, and we have the mechanically interlocked molecule. So the excitement did not stop there. The fact that the rings were not just sitting together willy-nilly, but were sitting in relative geometries with respect to each other meant that we could see, using the technique of dynamic nuclear magnetic resonance, first of all, this rocking motion between the red ring at roughly 45 degrees to the plane of the blue box. And this is happening about 2 million times a second at room temperature. The next one, in terms of rate, much slower, is this one, where the red ring pirouettes around the blue ring. And you see it going, I guess, anti-clockwise to begin with, and now it's going clockwise. We can't control that phenomenon. It will go in both directions. And this is happening about 2,000 times a second at room temperature. And then the third one is a circumrotation of the red ring through the blue ring, which is the most devastating in terms of breaking all the non-covalent bonding. And so, and again, you can see it could be anti-clockwise or clockwise. And so it's by far the slowest. It's happening about 30 times a second at room temperature. And I think it was the realization that we'd not only made a mechanically interlocked couple of rings, but these rings were so subtly talking to each other that it didn't take a lot of imagination to think we can turn them into switches and ultimately maybe into machines. So the next one that came on the agenda was the equivalent of catenane, a degenerate 2-ritaxane. And so this is the same story as you've seen with the catenane, except our template this time is a dumbbell. And I just happen to have drawn it like this. It is very much more, excuse me, flexible. But again, with a little patience, the same situation unfolds. Form a covalent bond, switch on the recognition of this with that, and you have formed here the recognition between the red and the blue, the donor being the red and the blue being the acceptor, and form this next covalent bond, and we'll complete the weak interactions, but we'll also form a mechanical bond. And we have a 2-ritaxane that, well, because this is not so well pre-organized, we don't expect it to be as efficient as was the catenane, and true enough, about half the yield. Remember 70, now we get 32%. Now, if I draw this slightly different, before we go here, here's my movie for this one. So it likes to cuddle the one with 2 positive charges, and the same routine, it's knocking out, if we go back to the beginning again, the bromine from here, forming a covalent bond, and then it's interacting and forming the second one, and now we have the 2-ritaxane. Okay, so this degenerate molecular shuttle can be drawn this way, and if we do, then you can see that it doesn't matter whether the box is sitting on this left-hand red ring or on the right hand, they're the same. You just move them through 180 degrees. And this particular movement is occurring roughly 2,000 times a second at room temperature. And now one can think in terms of linear movements of more than a nanometer overall. And here is, again, a movie showing effectively how this might be happening. As I say, about 2,000 times a second, shuttling. So at the end of this very short communication in the Journal of the American Chemical Society, we had 4 sentences, and I'm not going to read them all out. I'm only going to tell you that the then editor of the journal said I should take them out. They were hype. And so I wrote back very kindly and said, please let us keep them in because I don't think they're hype. So I single out the second one, insofar as it becomes possible to control the movement of one molecular component with respect to the other in a 2-ritaxane. The technology for building molecular machines will emerge. So this was somewhat prescient, you know, in retrospect, and I'm glad that I didn't give in to the editor on that occasion. So the next thing was to take that degenerate shuttle and decrease its degeneracy to being, well, asymmetric, if you want another word. And so we replaced both red rings by another red ring, a biphenol here, and a so-called benzidine unit. And we knew from previous molecular recognition studies that the blue box would prefer to be on this ring much more on that one. And experimentally, it turned out to be an 84 to 16 ratio. And the next thing that was important about this experiment was that here's another of these movies just to make this point. So it's spending most of its time, 4/5 roughly of its time on the green, and only 1/5 of its time on the red. But the other thing about this system is, if we just go back and look at the chemical constitution, these are nitrogens to which we can add protons. And if we do that, we turn this entity into a dication. And if it's a dication, these 4 positive charges are not going to be happy, and the ring is going to move automatically, all of it, to this site. And so this is exactly what happens. In the presence of acid, all the ring goes and sits on the red. And it's only when you apply base and remove these protons that it will go back there. And so in 1994, we have a molecular switch. And this is a movie showing that. And so when this turns from green to this sort of brownish color, this is when the acid has visited it and turned it into a dication. And as long as that's brown, the ring will sit there forever and ever. When we bring some base and get rid of the protons, it'll come back and spend most of its time there. Okay, so I've quickly shown you how we've established a molecular shuttle and a molecular switch. The point is we're a long way away from making a molecular machine. Why? Because if you take a switch, so it could be anything that you see a switch, one to switch on electricity. You switch it on, you switch it off. No work is done. So how do we get to a machine? Well, the first thing we've got to do is come up with one or two so-called ratchets. One is an information ratchet, and I'm not going to talk about that. The other one is an energy ratchet, a flashing energy ratchet. And so this is where we devised a dumbbell where the stoppers are not big enough to stop the ring coming on and off, but big enough to sort of slow the passage down and to allow us to dictate a direction. And so here's your little blue box that you're familiar with. And we have a green neutral end here. This is a neutral end. And we have a charged end that is blue. And so I'm sure you'll all agree, particularly if you're physicists, that this ring is going to, if it wants to come on and recognize this Naphthalene unit, which it really does want to do, is going to come on from the left-hand side over the neutral end rather than over the charged end. And so you can speculate that that's exactly what it does, and that once we get to here and molecular recognition is in place, we can switch that molecular recognition off by reducing the charge here from 4 to 2 plus, but at the same time, we're only going to be putting in 2 electrons, and so to each of those, we create what's called a radical. And this is indicated by this purple unit, which is a plus and a dot. In any event, we switched off the recognition, and the ring will now come off by the right-hand side. We've reduced the positive charge. We've actually changed the shape of the ring such that it doesn't want to come off this end. And this profile here, in a way, summarizes what I've been telling you. So the blue rings come on, and they go into this energy well, where they're happy. And then unhappiness visits them when we reduce them, and they're lifted up here, and we bring this mountain down, and they leave by the right-hand side. And so we've made a very simple flashing energy ratchet. But we don't have a machine. We lift a ring out of solution, and we plonk it back into solution. I guess I'll have another of those movies. Yes, here we are. So here it comes on with its 4 positive charges. It likes being on here. We reduce it, it becomes purple, and it goes off this end. Once we oxidize, it'll come back on here again, and it will leave once it's reduced from here. So that's unidirectional motion of the ring along this rod component. Now, we were very fortunate in more recent times, Northwestern, in 2010, this was a Lebanese postdoc and a Midwestern graduate student got together and did an experiment that we might well have done 25 years earlier. We took paraquat, which we got here, remember way back, the wipeout weed killer, and the blue box, and said, well, nobody has tried to see if we reduce all of these to radical cations, there will still be free positive charges, but there will be free radicals, and radicals tend to want to pair up, and so they might like each other to the extent that they will overcome the Coulombic repulsion. And that's exactly what happened. This turned out to be a very strong complex. So this was a major breakthrough, because it meant that ultimately, again, when we oxidized, we had enormous coulombic repulsion making these parts fly apart. And this allowed us to redesign our flashing energy ratchet. We put the positive charge on the left-hand side and the neutral one on the right-hand side. And by a series of reductions, relaxation, oxidation, and relaxation, we could drive it round in the opposite direction. So here's another of these movies showing you that when we have the so-called tris radical, free radicals, free cations, trication, we have this very strong one-to-one complex. Purple loves to go inside purple. But as soon as we oxidize, it wants to get out of there like a bat out of hell. Okay? And so this leads to the design of a molecular pump. And this is the blueprint in just simple cartoon form, graphical representation, if you don't like me using the word cartoon. Here is the blue box. And here is one of these positively charged pseudo-stoppers, not big enough to stop it coming on, it does. And now we're going to use this radical recognition. So we're going to be doing a reduction to bring it on here. And now we also have a steric barrier. You might call this a speed bump or the green door. And here we now have a collecting chain. So now we're not going to release this ring into solution. We're going to collect it. And if we can do that, we're going to have a machine. And so you see this movie down here showing you what's happening. Reduction, it brings it on, the ring, and then oxidation and thermal energy. It waits here for a while before it goes over here. Let's watch it again. This is the first ring coming on. Reduction, oxidation, thermal energy, it's here. And notice when the second one happens, this one wants to come back, but the speed bump stops it. So a huge amount of trial and error and elegance on the part of the design by the students only made this possible. I mean, I'm showing you what worked. There were 30 examples that didn't work the way this one does. Okay, so again, using another type of movie, you see it coming on. When it's purple, it's blue, it waits here, goes past the speed bump and gathers there. And then this wants to come back when it's reduced and again oxidized, the second one comes on. And so to summarize it all with these cartoons, it's simply reduction, oxidation, thermal energy to get one ring on. And you can call this, if you like, a two-retaxane, because now we have it locked on here. It's not going to leave. And repeat it, and we're going to have two rings and the dumbbell, namely a three-retaxane. So the movie again to show you it happening. And we'll see. So we're in the reduction phase here, bringing this onto the recognition site. It's oxidized, and now it's making its way over the speed bump to join the first one that is here. If we look at this again, reduction, then oxidation, all the charge, forcing it over the speed bump. It is here. The second one coming in reduction, this wants to come back, cannot, and it will be joined by that one. So that's our molecular pump in action. And here's just one slide to show you the chemical constitution of that pump in all its gory detail. And some so-called proton NMR spectroscopy that was done at 42 degrees centigrade in a deuterated acetonitrile that shows through movement of these signals that when we carry out the reduction followed by the oxidation, we get to this point here. So signals have changed quite a lot. And already there's some leakage of the ring over onto the chain here, because these are now what we call very high field signals. And if we wait an hour and a half, they grow in intensity until they can't grow any further. And all the ring is now sitting here. We can repeat this reduction process and the thermal energy following the oxidation. And we wait for another hour and a half to get through to the final Schreier taxane. And so, in summary, we can pump one ring followed by two rings. And in doing this, we're doing chemistry away from equilibrium. And this is just summarizing what happens and giving you some account of the efficiency. So the first ring is brought on with a 90% efficiency, reducing with zinc dust and oxidizing with nitrosyl hexafluorophosphate. And this number is quite important. The barrier to get over the speed bump is 23 kilocalories per mole. Weren't we overjoyed when we found that the next barrier to get the second one over is with an experimental error the same? So the message here is that once you have one ring on, it doesn't seem to have any influence over the rate at which the second one can join it. So it comes on with an 85% yield, and overall the 90 and 85 is a 77% yield of that Schreier taxane. And so now we have what I call a multi-stroke molecular pump in the making. And what I'm showing you here is just this energy level going up, because this is my only way of giving you proof that we are actually creating a machine, because every time we bring on a ring, the energy is increasing. And if I bring on the fourth one, well, we'll stop there. And each cycle traps one ring in a very high energy state. Some will be lost to heat, of course, and some of the energy input is trapped in a machine-like way. And finally, I can claim work is done. So what could this be useful for? Because that's always the question. And I'll try and keep this question at bay to some extent. I think we're maybe half a century away from looking at the utility of these new molecular engines, as I sometimes call them. It took the steam engine 50 years to get from conception to being used in factories and then in trains. We could be going down the same sort of route. But having said that, there are some glimmers of what can happen when you start to pump from two ends of a polymer chain lots of these rings onto a long polymer. And the outcome is that in this middle region, because of all this positive charge and the fact that they don't like or speak to the polymer at all, they're very unhappy. And because they're very unhappy, this leads to a material that is very subtle and has been, in another context, shown to be scratch resistant, and in a Japanese variety has been put onto the back of cell phones. So it has found the whole idea some application already. Here's a simpler movie just showing these rings coming on and how when they congregate in this long polymer chain and are unhappy to be there, we have a situation where we have unhappiness and therefore a material that will express that unhappiness. Okay, so we've been doing chemistry away from equilibrium, and I hope I've convinced you that the whole journey that I've taken you through briefly is exemplifying the fact that discovery is not yet predictable. To summarize, and I could go back to 1970, but let's just start with the shuttle at 1991, and then the switch in 94, and in the intervening period through 2015 to the present day. It should be 2018 now, shouldn't it? We have over roughly, or more than a quarter of a century, evolved this pattern. And these are, some of the main players that have been involved with the shuttle, the switching, and the machine. Just to give credit to a larger group of people, and although this looks male-centric, it happens to be that men seem to have liked to work on machines, whereas women have worked on other aspects of our research. We've been well funded through the years, and at the present time from King Abdul City for Science and Technology in Riyadh. I just want to make one comment to finish, and that is diversity pays off big time. Science is global, and science knows no boundaries. You can build walls, but science will get over them. Our group, over a 50-year period, has been in 6 universities. We're starting a group in Australia and New South Wales. I've spent time, 3 years in a company, and it's not relevant to my talk here, but I have 2 startup companies, and one of them, Panacea Nano, is producing this product Noble, spelled differently than Nobel, Noble, which are skincare products, cosmetics, and I've brought samples for those of you who might be interested in taking away. There's 5 of them there. And the other company is, believe it or not, looking at new ways of isolating gold from ore that avoids the use of cyanide. This is quite important in Montana. You are one of the most forward-looking states. As a state, I think you have decreed that the mining companies should not and must not use cyanide. So Montana is on our side. So as I say, I've been involved in 4 countries since I left Scotland 50 years ago, with 50 different nationalities and over 500 graduate students and postdocs. And so that's my story, and you said don't go over 45 minutes, so I'm at 43. So thank you all very much. Yes, sir.
We understand that you aren't going to try to do much in the way of predicting the future, but I think we have to wonder what kinds of things do you think molecular machines might be able to do? And specifically, if you see potential in the area of molecular computing, what kinds of advantages do you think that there might be to molecular computing over other?
Well, we visited molecular computing in the period of about 1999 through to 2007 with Jim Heath at UCLA, and then he moved to Caltech, and then I subsequently moved to Northwestern. Parenthetically, Jim was the student who discovered C60 as a graduate student at Rice, as a member of the Smalley Group, a remarkable physical chemist. And we came up at the end of 2007 with a 160 kilobit molecular memory. It was great, except that it would only cycle about 100 times. There was a lack of robustness, and so it seemed to, as it were, the parts shake itself apart. And it was based on a monolayer of rutaxanes trapped between a polysilicon wire on the bottom and titanium aluminium wires on the top in a crossbar type architecture. At Northwestern, we've been putting the catenated analog of this rutaxane into metal organic frameworks in pursuit of getting to a more robust house for them to live in. And we're getting some, I would say, feedback that is encouraging, but we've still got a long way to go. So I think, yes, there is a possibility of this machinery as switches, not as machines actually, as switches making their way into molecular computers. But you know, you've got to recognize that there'll be competition in the developing period, and so quantum computing could well be winning the race, who knows. So it's going to be interesting times. Yes?
First of all, thanks for the great talk. Is the bond energy of the mechanical bond essentially just bond energy of the covalent bonds making it, or is there some other stability or instability?
No, I always just say the strength of the mechanical bond is the strength of the weakest counting. It has to be not a peripheral bond like a carbon-hydrogen bond. We have to forget about those. It would be a carbon-carbon or a carbon-nitrogen bond or a carbon-oxygen bond. It has to be essentially the strength of the weakest covalent bond in that assembly. So we're talking about something that's as strong as a covalent bond. For those people who have used metals, coordinative bonds, which are now quite popular as well, it would be the weakest, either covalent or coordinative bond in the assembly. Yes?
I noticed you use a lot of polyether linkers.
Yes.
And for your pumps, though, you use alkyl linkers. And I was wondering, does that have an effect on the shuttling kinetics? Or what why use one?
Okay, so we avoided the polyether linkages in the collecting chain, as we call it, for the pump, because we did not want the blue ring to have any love for going on to that ring. We want it to be a hate-hate situation. Now, if we had the polyether chains, they would welcome the opportunity to wrap themselves round the blue box, and we wouldn't be able to sell it to the world as it would be a love-love situation, and that wouldn't be as good. So that was the reason for getting rid of them for the pump. But, going back in history, it's very interesting because the early people who tried to make catidanes and retaxanes were insistent in using hydrocarbon chains and hydrocarbon rings. And this was Ed Wasserman, who was once at Bell Laboratories and then eventually at the DuPont Laboratories, and of course now retired. I know that he was a president of the American Chemical Society somewhere later on. This was what he tried to do in 1960, and there is still some discussion as to whether he managed to do it, because if you get a 0 point and 3 or 4 zeros, I've forgotten the number, it doesn't really matter, 1% yield, you're not really going to take the world with you. So that's interesting. But I think you will see it's now interesting insofar as we do want to make mechanically interlocked molecules where the rings and the dumbbells don't talk to each other, because we see these material properties now arising. So what prevented the early, as it were, mechanical bond makers from success is what, in retrospect, we now want to get round and use. But we know that we're going to have to play tricks. We've got to use molecular recognition to make these things in the first place, and then some post-chemical modification to remove the love and make the hate come onto the scene. Yeah. Yes.
Really beautiful chemistry. Thank you for your contribution to the field and everything else. Related to that question, can you maybe comment on you talked about the dynamics of the macrocycle, and maybe you could comment on the dynamics of thread and how that affects both the synthesis and the properties of the
Yes, yes. There is a multitude of physical, let's call it organic chemistry, to be done here. The thread, of course, can be undergoing with respect to the ring, or the rings with respect to the thread, and whatever you say is it's a chicken and egg situation, the rings can be rotating around the thread. The thread I draw in these movies as being a rigid long rod. No, it's not. It's wrapped around all the time. It's very flexible. So yes, there's a huge amount of work that still remains to be done, both experimentally and I think a lot of it computationally, to be very honest, to throw more light on these subtle features. I'm teaching at the moment, and this topic actually came up in a related context on Friday evening or Saturday morning. And, I made the point to the students that as scientists, we have the opportunity to, after we've discovered something, we can stay with that very small something for the rest of our lives. We can dot I's and cross T's until the cows come home. or you come to terms with the fact that, well, that might not be the best thing to do. You better move on and see how much further you can go with the discoveries that you've made so far. So we made the choice to push on rather than to continue to live looking at the minutiae. I mean, there's another area that is wide open, and that is this little blue box is always, in our work, 98% of it used as the hexafluorophosphate salt, so with a soft salt. So it's soluble in polar organic solvents. If you convert it to the tetrachloride, this is a beautifully aqueous soluble material. And there's another chemistry there that somebody could start and exploit going right back to the beginning, and it will be very different because there'll be hydrophobic interactions. It'll be very different from what we have observed in polar solvents. And, you know, again, a lot of this is down to what you can persuade students to do. Yeah. Everybody wants to do something new rather than stay with something that, well, the last student did it. Yes. Yep.
I'm wondering if mechanical bonds have shown up in any biological systems.
Yes, yes. They're replete in both proteins and in DNA. I'm not very good at giving you absolute concrete examples, but I brought along a copy of our book on the nature of the mechanical bond, and they're certainly discussed there, particularly in the first chapter. So this is one of these fields which I think is very nice insofar as the growth in the field of chemistry has been, as it were, in step with what's happened in biology. I think we have many more examples, not that that means too much, but of course the elegance of the ones that you see in biology are just astounding. Yeah.
You said that there's energy stored when you stack the blue box rings on these threads and toxins. And then you said that some of these are being used as sort of shock absorbing materials in phones for screens and things. Are those two things related? Is the energy somehow up?
Yeah, I'm sure it is. I'm sure the molecular properties are being expressed at a macroscopic level, and we'll just have to wait. I mean, it's really early days to find out how the materials properties are actually related to these these molecular properties. But you know, already the Japanese are talking about slide ring polymers and say that they have a big future, and I wouldn't disagree with them. I think in material science, we're going to see a new field of polymer chemistry grow up as a result of the mechanical bond. And when I'm on the same topic, although I didn't mention it today, stereochemistry, if anybody's interested in stereochemistry, is another area that is revolutionized by the mechanical bond, simply because you bring, in Prelog language, axis of chirality and planes of chirality very much into the picture, and you don't need any asymmetric centers or stereogenic centers or whatever you call them. So there's quite a lot that's being brought that's new to chemistry because of the advent of the mechanical bond, and I'm sure is going to be new to material science, and probably we'll get some marriage with biology, and who knows what's going to happen in the next half century. Yes, sir.
I was wondering if this evening you'll talk about elective affinities.
If I'll talk about
Elective affinities.
elective affinities, you have to always define this for me.
Well, in that case, it's just a footnote
Yes.
to what you're doing. And as you may know, at the turn from the 18th to the 19th century,
Yes.
discoveries were made that if you had a compound
Yeah.
and an element,
Yeah.
brought them together,
Yes.
one of the components would leave the compound and connect up with that element. And there were cases where you had two compounds, A and D,
Yeah.
C and D, and they would connect with B
Yeah.
and with C,
Yes.
and B would connect with E.
Yes.
And elective affinity was just an expression of
Of
wonder and perhaps resignation. And Immanuel Kant, for one,
Right.
thought
Right.
that,
Oh yeah, the philosopher.
yeah,
Yes.
that chemistry would be nothing more than, that's not the word he used, stamp collecting.
Oh.
Because he didn't think it could be mathematically expressed.
I would not agree with Professor Khan. I have conceded that there is a lot of chemistry that could be described as stamp collecting, but I think the same is true in physics and biology and material science. I have also commented that a lot of chemistry, when it's written up, reads a bit like a telephone directory, and therefore not very interesting. But what I will point out, and I will probably make this point this evening if I can think about some of my last slides, is that I can make an argument for chemistry being the youngest of the sciences, or amongst the youngest of the sciences. This all broke at my feet in 1991. My co-laureate, Jean-Pierre Sauvage, in 1983. Ben Fring about 1999. So we're talking roughly about the last 25 to 30 years. And before that, there was not much to talk about. That's the first thing. The second point I will make very strongly this evening is, and this is by no means a first, Marcel Berthelot made the point back in 1860, and many have made it since, that chemistry is amongst one of the most creative disciplines that you can come across. And the reason is that we make stuff. We make our own materials, our compounds. And while you make things, you're in the same league as novelists, composers, painters, sculptors, you name it. And so there's room for every generation to come along and express their creativity in chemistry and cognate sciences at a very, very high level. So I don't preach the fact that, and you know, a lot of this comes because I was confronted, you know, I told you that I wasn't very happy these early days when I went to Sheffield University. There were 4 very arrogant professors who put out a message that chemistry was finished. They had done it all. And you know, if you've had a 10-year plus apprenticeship in the subject, and some of the older people tell you in another way, you've totally wasted your time, then I'm sorry, I got very angry. And I said to myself, I will show you that this is not true. Yeah, so I think some of our brethren have talked the subject down quite, I think, unfairly. It's open for much discovery, much invention, and much creativity for many, many years, decades, maybe centuries to come.
Just one more thing. There was a novel titled Electric Affinities by Goethe.
Okay.
And it's a story of 2 couples.
Yes.
And electric affinities is explained to them.
Yes.
The chemical
Yeah.
story.
Yes.
And in spite of being warned, it happens to them.
Right.
And then in blurb that he wrote for himself,
Yes.
in 3rd person, says that nature and science come from the same thing because nature is one.
Mm-hmm.
And so, as I said, it's just a footnote.
Well, no, I think I should spend more time delving into philosophy, and you know, I took a degree not in chemistry, but a degree in philosophy, didn't I, after all? So I should honor that situation even today. Yes. Richard, yeah.
One of your predecessors in the President's Lecture Series and another Nobel Prize winner was David Baltimore.
Yes.
And while he was here, he touched on the darker side of science and what some of the unfortunate, even tragic consequences of scientific research have been. I wonder if in the research you've discussed with us today, you have seen or considered any potential negative consequences.
You know, I've got to say that I've not, but then, you know, it's my makeup that I tend not to concentrate on the negative, and I tend to promote the positive. You know, I can concede, of course, that if one looks at the scientific scene of the last few centuries, there have been times when there have been discoveries that are hugely negative for humankind. I mean, I guess at the moment we're looking at a war in Syria with chemical weapons being used, and that gives the word adjective chemical a bad name. Well, of course, you know, I pointed out that thousands of compounds are probably being made every day, and there will be part of a scientific community that will not be able to stop themselves looking for chemicals that are not going to be very friendly to us as human beings, and that's most unfortunate. But I don't think we can use that situation to sort of tar the brush across the whole domain of chemistry or science. We just have to recognize that it is part of the human existence, and we would wish, I would think, to keep these dark sides under control. And, you know, there's no doubt, I mean, I'm not qualified to speak too much longer on this subject, but I think as a group of people on a planet Earth, this is one of our biggest challenges, be it chemicals or be it the physics that has produced nuclear weapons and so forth. It's one of the biggest challenges we face, to bring reason to bear on the various countries that step out of line. I would only go as far as to say that I do wish that we saw many more scientists in government. And so in this country, I actually interacted with someone who will be running for the American Chemical Society presidency at the next round, Louis Eschagoen, and he told me some of his goals. I said, is there any way the American Chemical Society could team up with other learned societies and approach a way by which we could fill Congress with scientists and engineers? And, you know, you can perhaps be dismissive and say there's no way it can happen, but the point is it's happened in China. And so the present Chinese president, and I don't necessarily, you know, lump out nothing but praise for him, but I do want to point out that he's a Tsinghua graduate in engineering who majored in organic chemistry. And his prime minister, Li Keqiang, or if I get the pronunciation right, is a Peking-based economist whom I've spent 90 minutes talking to. And these people are extremely well informed about a huge range of topics. And this leaves me very concerned at the moment for the Western world. I mean, they know what they want, they know where they're going, and they're very well educated. I better stop there. If you get me onto Brexit, then I will be completely out of control. Yeah.
Here.
Yeah.
Sorry. On that topic, what you made the point in your story also makes the point that scientific discovery isn't necessarily predictable. And in the research that you were doing early on with the weed killer, you know, it could have led to a whole bunch of things, but it led to the Nobel Prize for you. And I'm wondering, number one, do you think that there were things in your control that led you to that point? And number two, how do we defend scientific discovery that might not have an immediate point to those who believe in government that it should? You know, there's been movements against a lot of basic research because it
Yeah,
doesn't
yeah.
do good.
Well, I don't know which one to take first. Your first point is, was there anything that I worried about me getting out of control, you know, working at a company that was producing weed killers and found that a component of them, you know, put into another context, was no longer a weed killer, but was very useful in making molecular machines. I just thought it was a bit of a gift, and I look back on it and think if I'd not, in an enforced kind of way, because I wasn't in love with academia, gone to the industry, my story would have been very different. I probably would not have been here, to be very honest, and I would probably never have seen Stockholm. The other one I feel very passionate about, and I find that going around the world and being on the stage with fellow Nobel laureates, there's not, to my way of thinking, any exception to what I'm going to say. Everybody extols the virtues of a good component of just basic fundamental research. And the argument that a country does best if it supports people, rather than projects. Now, unfortunately, in the last few decades, both the politicians and I think in cahoots with some scientists have got themselves wrapped up in a belief that you can pinpoint through putting lots of effort into projects, science that will be revolutionary for a nation. They have it all wrong. Science shows that if you leave people who are your best people, and somehow there has to be some mechanism by which a lot of funding goes to the very able people, the people who've shown that they are creative and doing things that are liable to lead to new things, that is much more of a good investment for a country than the project-based one. And I maybe slip some slides in tonight of comments from other leaders. There is a great comment by the scientific advisor to Franklin D. Roosevelt. So we go back to 1945, which essentially says this, that the story of science has shown that the support of people rather than projects is a very, very much more wise way for a country to invest in science. And this has been my own experience. Although I have to say I've always had to take part in getting funds to do projects. But one way or another, running a big research group, there's been enough room to bootleg, if you want to use an expression. And, you know, I never prevent my graduate students or postdocs from doing things that just catch their fancy. And if they're successful, what do you say to them? Well, that wasn't the project you were on. I don't want to know. No, you don't. You congratulate them. And this company that is now taking off, there's a group of people coming to Northwestern on the 24th of May. They're going to invest $70 million in marketing these products. That's a 2-year miracle from the company being set up. The discovery in 2010 was totally serendipitous. The gold mining one, gold isolation one, was 2012, totally serendipitous. Fellow Scot Alexander Fleming in the mid-20s, working in what we now know as Imperial College London, noticed something in a Petri dish that became, well, it was the penicillin mold. And as I often say when I'm teaching students, you know, just look at the person on your right and the person on your left. Before the advent of penicillin and all the antibiotics that came from that, they wouldn't be there in the class with you. This has been transformative. Over and over again, serendipity, given to people working in an encouraging sort of atmosphere, will outbeat this planned research, which could be along the lines of, well, let's make a better solar cell or let's make a better battery. You know, I'm not saying there's no room for it. I'm just saying that I think that former type would probably serve most people and most nations better than this drive towards too much directed research. Room for both, but for heaven's sake, let's keep the door open for a lot of the fundamental stuff.
Well, you have satisfied the curiosity of our audience, so thank you very much.
It's been my pleasure. Thank you.